Now let's go to section 2, non-homogeneous linear ODEs with constant coefficients. Here's the general form of the ODE, and here is the initial condition, artificially created. Now, from the ODE, let's take a Laplace transform, and this is what we get. The left-hand side is the same as before. We have the input derivative formulas for the nth derivative and so on and so forth, first derivative and the original in the end. And the right-hand side, f of t is becoming capital F of s upon taking the Laplace transform. Now, the left-hand side is exactly the same as before, so we can do exactly the same thing as in homogeneous case to take the like term. And what do you get? We have to have the characteristic polynomial here, which is degree n. You see, an should not be 0 because this is nth order. Now, how about the others? This polynomial, R of s, has degree at most n minus 1. And then flip this to the other side and divide by q. What do we get? We have this rational expression, R of s over q of s, where R of s has degree at most n minus 1, and q of s has degree n, so this is proper. So we can decompose. Now, do you remember all this about R of s over q of s? Have you seen this before? Yes, of course. It's coming from right here. It's exactly the same thing as the fraction that we dealt with in homogeneous case, and its Laplace inversion is the general solution of the homogeneous equation. So we're going to name it as capital Y h of s, h for homogeneous, and this is the Laplace transform of the general solution of the homogeneous equation. Now, if you take the Laplace inversion, then you're going to get the solutions. This is a general solution of the homogeneous equation, and this is a general solution, general. So it has all the undetermined coefficients, which will be determined through initial condition, either something like this or some other numbers, whatever. Now, how about this red solution here, yp of t? It is called a particular solution, and p is for particular. And that one has no undetermined anything. It starts from f of t, which is a specific function, and then its Laplace transform is capital F. Again, this is totally determined. And then capital F of s over q of s. Q is the characteristic polynomial. Again, this is well-defined, specific, one function. And then Laplace inversion, and then coming back to this. So there's no undetermined anything here. In short, all the coefficients, all the undetermined coefficients are over here, and these will have to be determined through appropriate initial conditions later on. This one is just standing alone, and remember this. When you're doing this decomposition by partial fraction, you don't really have to worry about getting all the coefficients right about these because these are all undetermined. This one, on the other hand, you have to get it through because this one is specific, this one is particular. So all the intermediate constants that to be determined should be determined here. One more notational issue. What do you mean by this P? P is for particular, and I'm going to explain why this is called particular solution in a moment, but notational issue first. P is for particular, and that is the biggest reason I'm not using P here for this rational function here. Our textbook author is using P of s over Q of s, and I really hate that notation because it can cause heck of a lot of confusion because P is for particular, and we have red, and then we have blue. Which P is which is which? It's really confusing. This is terrible notation. So better avoid P, and this particular part is universal. If you look at some other textbook authors' notation, they still use P for particular. So this will have to change accordingly. So that's why I changed some notation from our textbook. So I risk a bit of a confusion because of that, because there's a bigger risk of bigger confusion. And of course, I told you the second reason, R is for remainder. Okay, let's come back to this particular solution business again. Why is it called particular solution? This yp of t is a solution of this equation, and this has nothing to do with whatever initial conditions you may or you may not be given. So when specific initial condition is given, under that condition, this yp of t probably will not be the solution unless you're extremely lucky, which has probability of actually 0. But if you look at only the equation, then it is a solution. That's why it is called particular solution. Particular in a sense that they are all particularly defined, but it's a solution nonetheless. Now, why is this a solution for this? Let's examine that a little bit. So consider this as a digression. This is a big topic from chapter 4, but let's cover it a little bit because at least to a certain degree you should know here, and of course some knowledge will be helpful in chapter 3 as well as here. Okay, all right. That's an equation, and then the solution is wrong key. Sorry about that. YH of t plus YP of t. So YH plus YP is a solution. So Y equals YH plus YP, and therefore this is a solution. So if I plug in this expression in place of all these Y's, then we have to have this equation because this is a solution, all right? So let's plug that in. So here, let's write this thing as YH plus YP, and then this is blue and that's red. Okay, this is getting too long, so let's remove this. Okay, so because this sum is a solution of this equation, once you replace this one in place of all the y's here, then you will have this equality. All right? And then from here, let's apply some algebraic manipulation. All these are derivatives, so we can separate them. It does not matter you take the derivative first and then add, or add and then derivative later. So we can separate all these. In other words, let's see. Okay. Okay. Almost there. Okay, and then plus. And then let's put those separated parts. Two more. Okay, all right. This left-hand side and then the left-hand side of this are actually the same because of the properties of the derivatives. You can separate the derivatives. Now, what is this quantity here? That's 0 because YH is a solution of the homogeneous equation. So this whole thing over here is equivalent to 0. So this part just drops down, and YP satisfies the original equation. The conclusion, YP is particular because it came from small f via capital F via capital F over Q, but also it's a solution of the given ODE. It, of course, will not satisfy the initial condition that you're interested in, or you will be interested in, but without the initial condition, it's a solution nonetheless. As for the initial conditions and so on, you can get those by determining coefficients from, determining those undetermined coefficients from YH. This one has all the C1, C2, C3, those kind of things. Okay, so much for theory, and let's try to implement it. And here's a problem. And I hope I have enough time for one problem. Let's try. So that's my question. That's my equation. And here is the non-homogeneous part, f of t. Okay, so y of s, capital Y of s is y h of s plus capital Y p of get that. And then what we want to do is take the Laplace inversion. Is therefore y h of t plus y p of t. And this is the direction we are trying to go. So this is coming from homogeneous, and that's particular. And then that's homogeneous, and then that's particular. The homogeneous has all the undetermined coefficients, particular has none. Okay, all right. Let's get the homogeneous part first. And then this is R of s over Q of s. And then R of s to be determined. And Q of s is the characteristic polynomial. So 4s squared plus 3s minus 1. And I'm going to need a little bit bigger font. And then let's decompose it. R of s over 4s minus 1, s plus 1. And then this can be decomposed like this. 4s minus 1 plus c2 s plus 1. Okay, all right. Now how about yp? And that is capital F of s over Q of s. I can't see it very well, so let's make it bigger. Okay, what is capital F of s? It's a Laplace transform from this one over here, f of t. So what's the Laplace transform of that exponential? E to the at is 1 over s minus a, right? That's the numerator. And let me highlight it in red. And the denominator is Q of s, and same as before. Let's highlight it in red. Okay, same Q of s as before. So we can decompose all that by partial fraction. Or let me see, s minus 1/2, it's better to have 2s minus 1 times 2 by multiplying 2 to each. So multiply by 2, we get 2. Multiply by 2, so we have 2s. Multiply by 2, this denominator will be gone. Yeah, that's a bit better. And let's highlight this thing to indicate that this came from over here, and the others are coming from the characteristic. Now, what is this? We cannot just leave it as is and then leave those as undetermined coefficients. We can't do that. Everything has to be determined here for this particular part. And you'll have to decompose this partial fraction, and you actually have to complete it. And of course, That's the kind of work nobody wants to do. So I'm going to use computer algebra system. Copy and paste, and I'll ask Mathematica to complete it. And this is what we get. So 2/15 s plus 1, and then answer 1. Let me write it like this. 4/3 2s minus 1 plus 2/15 s plus 1 and minus 16 fifth 4s minus 1. Now, among these, this is important because it came from the factor, this factor, red factor, this capital F, and of course it came from the original right-hand side. Now look at the others. This one and that one share the same. So this part, which I'm highlighting in blue, and this blue, actually is absorbed in homogeneous case. This one too. This one too. So this constant is undetermined, so it'll absorb this. So we can write the final answer like this. Taking the Laplace inversion, this one and that one. So k1 exponential of 1/4 t plus k2 exponential of negative t and plus finally this one. Let's see, 4/3 2s minus 1, so 2/3 exponential of 1/2 t. And this is particular, and these two are homogeneous. About these two, they don't do anything because they're going to be absorbed by these. And this one is important. It came from this new factor, which originated from capital F, which originated originally from the right-hand side here. This completes the problem. What did I do here? Did I get the same thing? Yes, indeed, the same thing. And here's the checking through Mathematica. It'll work. Yeah, we get the right-hand side. That completes the problem. We'll do other problems too, but in separate videos.